Hello, everyone, and welcome. Thanks for joining us for today's webinar on how to improve reliability using distributed model-driven FLISR without GIS. Presenting today's webinar is John Groders, Business Development Director for Grid Innovation at Minside ACS. John is a power system engineer with 10+ years experience in utility and industrial applications, specializing in distribution modernization. He holds an electrical engineering degree as well as a master's in business administration from Colorado State University and is a licensed professional engineer in the states of Colorado and Florida. Helping with the Q&A portion today is Rob Sadler. Rob is the Director of Business Solutions, overseeing technical pre-sales and product marketing. Rob's been with Minside ACS for about 21 years, so he's one of our resident experts. Just a few housekeeping items before we jump in. Should any technical issues occur, we will work to resolve those as quickly as possible. This webinar is being recorded, so all participants are on mute. The chat is disabled, but if you have any questions along the way, please use the Q&A button at the bottom of your screen, and we'll do our best to get to those at the end of this presentation. With that, I'm going to turn it over to John.
All right, thank you, Delana. Hope everybody is doing well during these trying times, but really appreciate you guys joining us. And like Delana said, we going to be doing several of these webinars over the next several weeks, so feel free, if you haven't already, to register to some upcoming ones. So today we're going to be talking about FLISR, which is a form of distribution automation to help try to improve system reliability. And then specifically, we are going to feature a technique of FLISR where we can use a distributed model-driven, but a model-driven that does not require a GIS import. And we'll talk about how we do that. So with that, let's go ahead and get started. And like Delana said, if you guys have any questions, use the Q&A feature, and we will try to get to those. We should have plenty of time at the end to address as many of those questions as we can. And if there's any that go unanswered, we'll certainly do our best to try to get those answers to you. Okay, so just a quick agenda and some of the objectives for today. We're going to compare, first do an overview of FLISR, but then compare some various types of FLISR methods. There are several out there, and we'll touch a little bit on those and kind of do some compare contrast on those. And then, like we said, we're going to highlight a model-based FLISR without needing GIS data. What does that look like? How is that implemented? And what are some of the advantages of doing that? We are also going to talk about items to consider when implementing FLISR. I mean, obviously, there's a lot of advantages, but some things that probably need to be considered up front and during the evaluation process that you'll want to take into account. And then we will talk about expected benefits. Obviously, we're improving system reliability, but really what are, from some successful FLISR implementations, what types of benefits did they see? And then, like we said, we are going to spend some time trying to answer as many questions as we can at the end. So with that, let's first start doing a little bit of interaction with you all. So of the utility attendees today, you'll get a pop-up poll here in just a second, but if you could answer which best describes where you are with distribution automation. So the different ones are none, you don't have any, and there's really nothing on the immediate roadmap. None, you don't have any, but you are considering something in the near term, maybe minimal, some small pilots or proof of concepts, or are you an advanced DA user where you have major deployments active on the system? So with that, we'll pop up the poll and we'll give you guys maybe 20 seconds to respond, and we will see what kind of the results are to have an idea of how diverse of a group we have today.
John, we went over 20 seconds a little bit where we saw some answers coming in, so I want to give everybody a chance to answer.
Oh, that's great.
Waiting for a slowdown. Okay, I think we're good now. All right, I'm going to push these out. All right.
Okay, so as expected, there's actually a very diverse group. The majority with minimal, maybe some small pilots and proof of concept, but looks like there's quite a few in all the other groups as well. So good to know. So we'll make sure to keep that in mind as we go forward, that we have, some very basic FLISR and DA users, and we have some of our more seasoned and advanced users. So great. Okay, so before we run, let's make sure that we're all on the same page of what we're talking about when we talk about FLISR. So just basics, you know, FLISR, we live in a world of acronyms, so let's make sure everybody understands when we say FLISR, we're talking about fault location, isolation, service restoration. Really what we're trying to do with FLISR, obviously improve reliability, but we were trying to minimize the number of customers during a fault or an outage by seeing if we can restore customers up or downstream of that fault. So in this very basic example, what we're gonna go through here is we've got a couple substation breakers on either side. They could be the same substation or coming from two different substations. And there's a normally open tie or switch in between them, and then some radial feeds going out there. So what happens is if we get a fault somewhere on this line, if the first fault clearing device is upstream at the substation, if this is just maybe a load break switch, the first breaker that can clear it is up at the substation. That is going to see the fault and clear the fault. But now we have taken down all the customers in those three segments. So the goal of FLISR or auto restoration is certainly to how can we restore customers on either side of that fault as quickly as possible in an automated fashion. So what we're going to do is first part of FLISR is fault location. So there's a number of ways to identify fault location of a fault, but the method we're going to be talking about today is utilizing fault flags. So obviously the breaker that cleared the fault certainly also saw the fault, so its fault flag is up. And then all the devices downstream, while they may not have the capability of actually clearing the fault, they can certainly see the fault, and they would raise their fault flag saying they saw it. Now, if this would be the last device that actually saw the fault, because it's the last one upstream of the actual fault. So we therefore know, okay, it's somewhere, that fault is somewhere in this segment. So the next part of FLISR is the isolation. So what the scheme is going to do is open up those breakers, isolate or switches, whatever you have there, and isolate that fault. So then we go on to service restoration, and this happens in two parts. The first part is relatively straightforward. It's upstream service restoration, and because we know the fault is isolated, we're going to close in that substation breaker and restore those customers upstream of that fault. Now, downstream restoration isn't as intuitive because now we have to make sure that we have capacity to restore those customers from an adjacent service and be able to bring them back online. So the FLISR algorithm is going to look at how much load was on that segment prior to the fault, and then look at what the current loading is on this circuit, and assuming that there's capacity to add it, then we are going to bring those customers back online. Now, the goal of all of this is to try to handle this, and we want to do it automated because if we can restore the customers upstream and downstream of that fault in under 5 minutes, then those customer outages are considered momentary. And we typically don't have to include those in our system indices. So very important to try to do this in a timely fashion. So continuing with FLISR overview. So FLISR has become, pretty much the industry standard, but it didn't always be that way. In fact, a lot of our products and everything still reference FDIR, simply because that was kind of the acronym that was used, 15, 20 years ago when we started in this world, and it seems like the industry has migrated more towards FLISR being the common one. Another one that I've seen is FISR or FISR. And then more generally, self-healing, auto restoration, all of those kind of. So when we're talking about that, we're talking in essence all of these, meaning virtually the same thing. So as we've said, the primary purpose is to improve system reliability, and we measure that often by various industry standards. So that could simply be number of customers interrupted. You add minutes to it, and then now you have customer minutes interrupted. And then some more common ones are SAFE and SAIDI, System Average Interruption Frequency Index, and system average interruption duration index. Now, both of those last two are the ones that if we can get as many customers restored in under 5 minutes, typically we don't have to include those in those numbers, and that is where you will start to see some dramatic system indice improvements. And there's a lot of things driving this, obviously. We're seeing a lot more action of people wanting to do more distribution automation, but certainly there's a push for tying new rates or tariffs into system reliability and therefore FLISR. One commonly used term that I've seen more and more is something called performance-based rate making, or PBR, and not to be confused with the bitter light beer PBR. So let's compare some of the different FLISR implementations. So the first one I have on here is just a manual approach, which obviously we wouldn't really consider FLISR, but it gives us a good baseline for how we would do maybe a system reconfiguration. So obviously, if it's a manual, that's either you can still do, operate your devices potentially manually and remotely, or you may actually have to physically go out there. But regardless, it's going to be a slow process, and there is no, typically no communication, and certainly nothing automated, and no model used. So as we kind of go up the chart of sophistication, the next would be a rules-based or a scripted approach, or using logic to determine how to reconfigure the system. Now, in that previous example, it was quite straightforward. You could certainly have probably programmed some logic either into like a substation controller or into the individual devices, doing like a peer-to-peer, and be able to figure out how to reconfigure the system. So you are not using a model, but you're limited on how many different iterations you can, because it all starts from a normal state, and then as you get to more complex schemes, it just breaks down as far as how much you can do as a rules-based system. So then you start to get a lot more sophisticated, and this would be an automated approach using centralized or DMS or ADMS, and you are getting your model. You're actually bringing in a model from your GIS. Traditionally, this is a pretty high cost endeavor. Now, there is a lot of advantages of bringing in a GIS model to be used as a real-time system model. Certainly, beyond just FLISR, there's a lot of capabilities with being able to do load flow analysis, state estimation, and such. But if all you're looking to do is FLISR, this may be a cost prohibitive approach for you. So one last approach, and this is one we'll highlight here in a second, is an automated decentralized model approach. So it's a decentralized model, and it's a distributed architecture. And we are using a model, but instead of doing a GIS import, we are going to build a much more simplified distribution automation model that is specific to the use cases that we are going to be using it for. So why, we've got all these different ones. Some use a model, some don't, and then which models we use vary. But why do we want a model-based automation approach? Well, let's move to a little bit more of a complex scenario where this would just only a model-based implementation would be able to handle something like this. So we have now 3 different feeders with some normally open switches in between. Again, could be coming out of the same substation, different substations, what may have you. But we are going to have a fault on this bottom feeder, and the first fault clearing device will be back at the substation. We will take down that entire feeder. So just as we did in the exercise previously, we want to start going through the entire FLISR process. So after all the protection, so if you have any reclose enabled, after all that, once we've gone to a fault trip to lockout, that's when you want the FLISR system to take over. So once we get that and we're taking over, we're going to look at fault flags, and we will find where the fault is, and that's in that second segment down line of that 3rd feeder. We are going to isolate that fault and then start with the restoration process. So we start with doing an upstream restoration. bring back all those customers closest to the substation. But now as we are looking, we're going to start to look at how are we going to restore all these loads downstream, and which source are we going to use to do it. As we look at that, perhaps there's another fault on the system. Maybe we're talking about during a storm condition and we're going to see multiple faults at a time. Well, this is when, maybe a rules-based system would start to break down, just simply because there's so many different iterations that it would just be really tough to account for. But if you're using a model-based implementation, you're always going to be using that real-time model and real-time situational awareness to know what the best way is to reconfigure your system. So let's go through the process. So we have a fault. Perhaps this is an actual recloser that can clear that fault upstream of that device. So we are going to clear that fault. Next step is obviously isolating that fault. So we've now have it isolated. But now here's a situation where we have all of these downline customers that are not in faulted segments, but we only have one source to feed those downstream customers. So we look, and at this current situation, we have 290 amps capacity on that first feeder. But if you could do the math, we need 330 amps needed. So instead of just saying we can't restore any, what we will do is try to restore as many as we can. And by doing that, we are going to open this, this switching device. And then we're going to start restoring as many of the customers as possible. So really, this is meant to show, the true importance of having that model-based system that can handle dynamically a changing environment, changing load conditions, and be able to do as much restoration as possible on your system. So let's move on to what we're featuring, and that's a model-based FLISR without needing GIS data. For us, it's a product called Centrex that we started to develop about 10 years ago, and the first Centrex system went live about 8 years ago. And since then, we've had tremendous amount of field success and some of the largest FLISR deployments in North America with it. So what does it look like architecturally? Because we said it's a distributed approach. So architecturally, this is what it would look like. It's very scalable. You'd have multiple servers communicating, well, depending on how many feeders, multiple servers, but they'd all be communicating back to your centralized system. Your SCADA, DMS, that could be Prism. If you're an ACS customer, it could theoretically be anybody's SCADA or DMS system. These Centrex servers then would therefore be communicating directly with all your IEDs and smart devices out in the field. These servers can be geographically distributed, or they could be in a centralized location. They could also be virtualized. So the architecture can look a lot of different ways depending on what your capabilities are. But what this does is this allows for a very scalable approach. You can start with a handful of feeders and work your way up to over 900 feeders like Georgia Power has done with this. So it really does provide that flexibility and scalability. Device interoperability, I assume most of you have quite a few different devices already out in the field. As long as they can communicate and you have that communications infrastructure out there, we're indifferent to what devices you have out there. So we can work with any of those devices, and pretty much anything. If you're speaking DNP, we can work with it. So how do we build this simplified distribution automation model? So for us, what we do is we configure a template. So this is our configuration, our Centrex builder. This is one of the templates, one of our more basic templates, where it's got 20 different feeders populated with a lot of different devices on it. And what we do is we take each one, we can highlight the feeders as needed, so we know which feeder we're working with at any given time. And then say for this example, we just want to use the first 5 feeders. That's going to be our island of configuration that we're configuring right now. So then we go through, we start naming the feeders, giving substation, the substation name. And we start walking through this template, provide some transformer data, And then we start selecting which switches and devices we want on there. We will build your different device profiles for you depending on what devices you have out there. And then you give it some basic parameters to work with. And then here is where you would put in your impedance data for the various line segments. And if you wanted, you could add other load information like number of customers on each segment. Therefore, you could do some real-time analysis of customer minutes interrupted or customer interruptions in general. So that's the first step of our process, is configuring that template. Next, we have to do a device configuration. So this would be looking at all your different devices, and we have to put in, all the different communications parameters associated with those devices. We can build, a lot of different device profiles for you, and then depending on your DNP mapping, we would match up the various points that you are going to need to be communicating, such as, bringing back telemetry data, as well as switch status and fault indication flags and such. So once we have done all of this, we do a import. We use our import tool, and we build a specific model for what we're looking for. So this is just using our packaged user interface. But again, since this can work with really any other system, all this automation process can just be handled underneath in any user interface you're already using. So with this, what we're just quickly showing is a fault on that middle feeder in between those two devices, and watching how first we are going to look for where that fault is. We receive the indication that we've got a trip to lockout. We know where it is, so we start to isolate that faulted area. We're going to do the upstream restoration, and then now we're to a point where we have to decide which feeder, either on either side of it, has the most capacity. Once we run those load flow analysis and the various FLISR algorithms, we will then therefore restore using the best possible source. And there we've completed our downstream restoration process. Okay, so let's do another poll. So in just a second, you'll see a poll pop up. And again, of our utility attendees today, which would you consider the largest barrier to deploying distribution automation on your system? So would you say it's inadequate communications infrastructure, or perhaps inadequate distribution assets? Maybe you just simply don't have enough switches and devices in the field. Or would you say, operations hesitation for trusting various automation techniques? Maybe it's a cybersecurity concern. Another one we've heard is, creating that compelling business case. So with that, let's pop up the poll and give you guys some time to respond.
Some of these folks are really quick on the trigger here. They're still rolling in. Give me just a sec.
Yep, no worries.
All right, looks like we've come to a slowdown. I'm gonna end the polling and share these results.
Okay, again, pretty diverse, but certainly not having the communications infrastructure and not having the amount of assets are leading the way. So that's interesting. But it's also pretty consistent with a lot of what we find is a lot of distribution utilities would love to do more automation. They simply are, to a point where they do need to add that infrastructure in place before they can really do more with it. So very good. Thanks for participating. Okay, so let's just talk really quickly on some items to consider when you are implementing FLISR. So obviously, first and foremost, safety. Anytime you're talking about doing any sort of automation on a distribution system, certainly safety for your utility personnel, but also for the general public, has to be the utmost priority. So, you need to be able to ensure that whatever system you're using, you can still leverage your normal tags, whether you're doing lockout, tagout procedures, and any sort of disable. So hotline tags, reclose disable, remote disable, disabling transfer, any of these all have to be considered when you are talking about automation to make sure that you're not jeopardizing any safety concerns. Communication, just like the poll said, you do need a robust communication infrastructure in place. And then also you need a heartbeat to make sure that you have that connectivity to all the various devices. And then also, will your FLISR system, if parts of your network go down, does the whole FLISR system go down, or can you just disable the portions that you've lost communication to? So just some things to think about there. Protection, when you're in a reconfigured state, you may want to send new protection settings to maintain proper coordination. What will your FLISR system do that? Will you maybe rely on the devices being smart enough to know that they've been reconfigured to change their protection settings? Some certain things to consider. How about distributed energy resources? That's certainly a consideration for any of you doing distribution operations or planning these days. How is DER going to affect it? And we'll do an example at the end where we actually incorporate DER into that previous example. And how does your FLISR scheme take that into account, and what are some of the things you need to think about? Critical loads, are there critical loads in your system that need to be taken into consideration or give prioritization? Maybe first responders, hospitals, all good things to be certainly considering when you're looking at implementing more FLISR systems. So some expected benefits of implementing FLISR. Obviously, improving system reliability is key, but let's look at some actual case studies. The first one, it's a little old, it's 6 years old now, but the DOE did a really nice report. And at the end of this, Delana is going to send you a link where you guys can actually get this report. And what they did is they analyzed 5 different projects that have already implemented FLISR, and they actually looked at 266 specific FLISR operations and did some quantitative metrics with them. So certainly they found reduced number of customers interrupted. In those number of operations, they estimate about 270,000 fewer customers suffered interruptions, and they're talking about longer term, not momentary. So you want to keep those under 5 minutes if can. Reduced outage impact. Obviously, customers experienced a lot fewer minutes of interruption. So 38 million fewer minutes interruption. So if you're having a hard time driving a business case, just think of the amount of revenue that can be saved by getting more customers on quicker. But then also some other indices that they saw were that reduced the number of customers interrupted by 45%. Also reduced customer minutes of interruption by up to 51%. Of an outage event. And these are pretty typical of industry standards. A successful FLISR scheme will certainly provide a lot of basis for improving your reliability indices very quickly. Another chart that I found compelling out of this was they looked at all those different events and they wanted to do a breakdown of the causes of them. As you could probably imagine, a good portion of them are vegetation, but then it's pretty diverse as far as other whether it's equipment failures, underground failures, lots of different causes for to start these FLISR events. And then we'll talk specifically about our largest Centrex deployment, which is Georgia Power, and they have and again they started this in 2012, and they've scaled it from just a handful of feeders to over 900 feeders now, serving over 2 million customers. They're even seen improvements on their SAFE and SAIDIs, both of them by over 35% on the circuits that they've upgraded. Another fascinating stat was from 2014 to 2016, they estimated 67 million customer minutes interruptions saved. But just in one day during Hurricane Irma, they estimated that they saved 82 million customer minutes of interruption. And also, they also estimated that they restored nearly 79,000 customers automatically during Irma. So certainly some very successful deployments out there. This is one of the largest FLISR deployments that I'm aware of in North America. So we're going to end with how, now that everything we're doing in distribution, so much of it we have to think about, okay, now that we're dealing with a lot more distributed energy resources coming onto our systems, how is that going to be handled? And FLISR certainly is no different. So let's look at that last scenario that we looked at, but now we've added some various DER devices. Now we will assume for this example that we will have active communication to either directly to the inverter or at least to the point of common coupling, maybe a recloser of where that distributed energy resource is located. So we will start the exact same example that we did prior and see how we would want to, how DER would potentially adjust how we need to think about this. So we have a fault on that same breaker or that same feeder, and we're going to clear it with the upstream substation device, and we are going to take down that entire feeder just as before. So the next step in the process, now obviously there is a lot of interconnection agreements and interconnection protection settings that are all taken into account that on a de-energized line, obviously the utility is forcing everybody, whether that's a utility-owned asset or a third-party owned asset, you have to take those offline. So obviously there's a lot of that in place, but we are increasingly getting customers asking us, well, we have that in place, but we also want that direct communication path to the automation system. And when there's a de-energized line, we also want them to make sure that there is no backfeeding on that de-energized line. So that is the first thing that can be incorporated into the FLISR system, is simply that reassurance that those devices are not feeding a de-energized line. So from there, we'll continue. We want to isolate the fault. So we have done that. We have done that here. We've isolated it. And now we want to start looking at doing the rest of our restoration. So we are going to do an upstream restoration. And again, the next part would be looking at doing the downstream restoration. So downstream restoration, in our middle feeder, we have 60 amps capacity. So clearly not enough to do much with it. But we look at this other feeder and we have quite a bit more capacity. So how can we use that to bring back some of these downstream loads down from it? So the next step in the process would be if we have direct communication with the inverters or have some metering data where we know how much all of these DERs that are now offline, we will need to know how much were they generating prior to that faulted condition, because we need to now account for that, because instead of the 70 amps, that was just the net load and there was some mask load in there. So if we have that communication, we know how much generation was occurring prior to that fault. Well, that's what our FLISR downstream restoration algorithm has to take into account. So instead of 70 amps, we really need to account for 100 amps if this was providing 30 amps of generation. And maybe the other PV device was adding some generation as well. And we know how much that was. So now we need to account for that. So now when you take into those new numbers, we realize that we won't be able to restore all of these customers, but what we can do is try to restore as many as possible. So we will first try to, we'll close this breaker in, temporarily have a loop feed, open that breaker, and then instead of being able to restore all of these, we will just restore the customers we can and bring back as many downstream customers as possible. Now, the last step of this would be customer specific, how you want to handle it. But perhaps once you get back to an energized part of the system, maybe you will allow those DERs to come back online. Maybe you won't. Maybe you'll only allow the ones that are upstream that aren't in a reconfigured state. Maybe those won't. But that would be a customer specific instance, and you could then therefore potentially send a command to allow those DERs to come back on after a certain given amount of time. So with that, that concludes what we wanted to go through today. Hopefully you learned something. Just a quick announcement that we have several of these webinars upcoming. Just go to our events page on our website and feel free to register and sign up for any upcoming webinars. And then with that, let's see what looks like. We have a few different questions coming in. So as you guys can think of some, or if there's anything, just feel free to send them in now. But the first question, and I have Rob Sadler with me, who's going to help us go through some of these questions. So Rob, I think you can take the first one. It is being asked, how does our system handle loss of communications, either to one device or potentially multiple devices? So if you...
Yeah, thanks, John. So certainly safety is paramount, as you mentioned, when we're anytime we're doing kind of automated switching on the live network like this. So loss of communications is certainly something we want to help make sure that we avoid any incorrect switching actions. So if we do in fact lose communications to a device that's part of an active automation scheme, we will disable the FLISR application and automation for that particular circuit. As you touched on earlier, the islands of automation will include multiple circuits with potentially multiple tie points. And so if we do lose communication, say for instance to a single device on a circuit or devices on a single circuit, we'll disable FLISR, but only for that circuit, and leave it active for the other circuits that are part of that island. So we'll be able to continue to isolate and restore faults to the extent we can, given the alternate sources that are still available. If we lose communication to multiple devices across multiple circuits on that island, then we may end up disabling automation for that entire island. And then, so if those devices go out of scan or don't respond for any reason, and then they do come back in scan at some point and begin reporting again, then the system can automatically enable those circuits again. And of course, if a communication is lost to a device, say during an active switching, restoration in response to a fault, the system will stop the plan at that point when communications is lost and take no further action. And of course, all of those events with regard to disabling or enabling FLISR on the system are the operator is notified of all those things as they happen through standard event and alarm messages, so that they're constantly aware of the status of the system. And then of course those alarms and events can be sent upstream to the SCADA system that the system's connected to.
Okay, no, great. Another question that came in, I can handle this, Rob, but if you want to add on to it, how do you handle more complex topologies like loop feeds, etc.? So what we actually showed, we only showed you one of the templates that we have in one of our more basic templates. We do have other templates that you can use to incorporate loop schemes. You can even, we have some templates that now you can incorporate all your DER points in there, or if you wanted to do integrated volt var control as part of your automation, though we have other templates to handle that as well. So the answer is yeah, we can handle more complexity. You would have to use one of our other templates to build those islands. And Rob, if you have anything to add to that.
No, I think you covered it, John. That's a pretty good answer.
Okay. Another one regarding comms that has come in. So since comms and real-time comms are paramount here, are some networks superior to another? For example, does a point-to-multipoint network give better response time and automation capability versus a mesh system? So Rob, if you want to just give your, I mean, I don't think that there is a right answer for that one. I've seen successful approaches, but
yeah, I'll give some thoughts. I mean, obviously,
okay.
we've seen, we've seen a number of different types of networks, and our system is flexible enough that it can support different types of communication networks, as you touched on. Certainly, latency is the primary, driver here in importance in terms of safe switching and performing restoration. So of course, the faster the turnaround time between control commands and responses, the better off we are. Our system does have flexibility in terms of being able to be tuned to a degree to support longer latencies with some systems that may have a longer turnaround time. Certainly, probably a more deterministic point to multi-point network is probably going to give, the best overall, performance and speed. Although the more modern mesh networks that are being, built with quality of service and some deterministic capability to support automation certainly have the capability to support this system. So again, like you said, there really is no single right answer for that. But as long as it's fairly low bandwidth that's required, so as long as the system can support latency requirements, then we should be able to deploy FLISR on it.
Okay, great. Another quick one that just, will this recording be made available? And yes, the answer is we'll I believe you'll get it in an email, the link, but certainly we'll get that to you so that you can watch this or share this recording as necessary. Another one that came in regards to energy storage. Have you considered energy storage as a source? And if so, how does the capacity and discharge rate get considered in the scheme? So there's a lot of ways that you can incorporate energy storage. As a source would probably be the most complex way. Certainly using it as a way to potentially alleviate load. So if you want to maybe restore more of another network, and you could send some different charge or discharge to a storage device, that would be one way. Using it as a source, yes, we have considered, yes, we do have some customers that are talking about doing some proof of concepts with this. The other part of it is obviously at that point, you would need to have I'm assuming you're talking about kind of a completely islanded situation from the utility. And at that point, you would have to think about having a grid forming inverter along with it. So the answer is yes, it would be complex, but it certainly could be done if the infrastructure and everything was in place. And how we would have to, and to answer the part that, yeah, you would have to take into account your capacity and discharge rate to be able to know how long you could potentially island parts of the system. So the answer is yes, it's certainly being considered and it could be done, just requires some complexity. Okay, next one that I see coming in is how do you handle when there are volt-var equipments in the enrolled feeders? So I'm assuming you're talking about, which one takes precedence at whether it's the FLISR that would take the precedence, or if how do we handle volt-var? Rob, do you want to kind of address that with how we would handle if we have two different distribution automations going on? Which one would take precedence at which times?
Yeah, so I mean, we have templates available in addition to the one that John showed during the example that allow the definition of regulator and capacitor controls on the network, so that the same system and the same model can be used to support integrated volt-var control, and so with the objective of flattening the feeder voltage profile and lowering that voltage. And of course, the advantage of this being a model-driven solution is that even when the feeder topology has changed due to any FLISR switching, we can still continue to attempt to optimize the circuit given the volt-var controls that are available. So obviously, we'll give precedence to restoring customers when a fault has occurred, and then following the fault and reconfiguration, we can then take a look at the conditions on the circuit according to the IVVC objectives, and then see if there are actions that can be taken by the system to re-optimize based on the new feeder topology.
Okay, great. So yeah, if you guys, it looks like we are getting a few more coming in. So if you guys do have any other questions, certainly run them in. Another one, and Rob, if you want to kind of address this, how would you modify the model when there is a change on the system topology? So I'm assuming maybe a permanent change, or you're adding something to that. How would we adjust a model on those feeders?
Yeah, that's a good question. So it's fortunately with this system, it's a pretty simple process because it's template based and we're not having to import the source from a geospatial model. The templates, as John showed during the example, are built with typically more circuits than you would probably deploy on a particular island, and then overpopulated with devices, more devices than you typically would see on a distribution circuit. And so you have flexibility when you're defining the islands and defining the circuits to choose, where those devices are and which ones you actually want to include in the model and which ones you don't. So if it's at a later point, say add or remove sectionalizing devices to a circuit that's already automated, you simply open up the tool, you make the changes in the tool that John showed to either remove the device or add a device, select the specific type of control for that device location, export that model and re-import it to the system, and you're up and running again. If likewise, if you say add a tie switch and add a circuit to an existing island, you simply need to then go into the tool, select the new circuit that hasn't been used as part of that template, define the devices just like you did when you originally built the island, and again export and run that import process that builds a model and takes only a few minutes. So it's a pretty simple process to make changes to an existing island, whether it be temporary or permanent.
Okay, good. Another question just came in. Where and what hardware runs the model? All devices have comms back to that location. What about redundancy? So I'll start to answer, and then Rob, I'm sure you'll have can add on. So the hardware that runs the model can be a lot of different things, as we showed in that system topology slide. It could be certainly on-premise hardware that could be centrally located. Those servers could also be distributed. I mean, you could physically have those servers at various strategic locations closer to the islands that they're automating. So there's quite a bit that can be done. And then yes, all devices will need to have communications back to that hardware, certainly. And then as far as redundancy, yeah, you could certainly have redundant servers, especially if you're doing something back, in a centralized location, or even distributed. You could have redundancy of those servers, and all those servers could also be virtualized as well. Rob, if you want to add on anything to that.
I think you covered it pretty well. Yeah, due to the templatized nature, the way we build the model and the system, that gives you that flexibility to, if you need to, primarily based on, say, your communication infrastructure and availability of communication, to distribute the application on the servers within the substation or different territories. I mean, if you do have communications that all terminate at the control center, so all of your field devices that you'd be communicating with all communicate back to the control center, then the hosts, and they can be redundant with automatic failover, can be deployed at the control center. If you only have communications available in a portion of the network, say, from a substation outward, or set of substations in a particular area, then you can deploy the hardware out in the field at those locations. So it's flexible in that sense.
Okay, so I think we've gotten all the questions answered that came in. If you have any more, you want to hear more, feel free, visit our website, acspower.com/feeder-automation, and feel free to reach out to me, either call me or email me. Would love to hear about any potential solutions that we can offer you. And yeah, this is what we do for a living. We love doing it, so love hearing more about what you guys are doing out there. So with that, looks like there actually came in one more right here at the end. Do you interface with SCADA or have a real-time GUI, a user interface? So I guess the answer is both, but Rob, do you want to talk more specifically to that?
Yep. Yeah, I'd be happy to. So our system is agnostic with respect to SCADA. The no SCADA system, is required to deploy to deploy the solution, obviously you have to have the infrastructure and the communications. But if there is an existing SCADA system, then yes, we have essentially a software RTU that's part of our Centrex host that facilitates real-time communication between the Centrex host platform and the existing SCADA system via DNP over IP. So it doesn't require any type of more complex interface, whether it be ICCP or multi-speak. It's a simple DNP link. So all the real-time information and commands are exchanged between SCADA and Centrex via DNP. And of course, the real-time GUI you saw during John's presentation. So when you saw the island with the 3 circuits and colorization, that actually is a GUI that's available. Again, it's intended to be an autonomous system, so there really is no operator interaction that's required, with the exception of the automated return to normal feature. But that GUI is available as a part of the system just by virtue of the way it's architected. So if you can operate the system just from your existing SCADA system, or you can also make our GUI available to operators if you want to use it to monitor and control the system directly there.
Okay. So I think that's probably brings us to a conclusion. Again, if you have anything else you need from us, never hesitate to reach out. We'd love to hear from you. Stay safe out there and look forward to seeing you guys in person down the road, hopefully sooner than later. Delana, do you have anything else to conclude us?
No, I think that's it. I did push out some links on the chat, but I will send those out in the email also as a follow-up to this webinar. Hopefully we'll see you guys on the next webinar. Thank you so much for joining us. Have a good day.